All right, today's lesson here is on bond polarity. And bond polarity refers to the word polar. Some molecules are polar, some molecules aren't. And so in chemistry, a polar molecule is one that basically has opposite charges. It's got a positive end and a negative end. And some of those molecules are polar, some of them have charges, others do not. To find out whether or not a molecule is polar, there's two things we have to look at. And I'm just looking at this today in this lesson. First, we have to look at the types of bonds that hold a molecule together. Meaning, if I have a molecule here, A bonded to B, the bond holding those two atoms together is what I'm talking about. There are different types of bonds, which we'll get to later, where you have, let's say, another molecule here, and there are bonds between those two. Those are different types of bonds, which we'll talk about further down the road. Okay, so anyways, we're going to look at how bonds holding a molecule together influence whether or not a bond is polar or not. The other factor that determines polarity is the shape of the molecule, which you can determine by using Vesper theory, if you've learned that from before. Okay, so like I said, let's look at the bonds holding a molecule together. There are, actually in grade 9 and 10, you were taught that there were two types of bonds, ionic and covalent. What I'm going to say is that there's actually two different types of covalent bonds. Okay, there's ionic, that's fine. The two types of covalent bonds are called polar covalent and nonpolar covalent bonds. And so to tell if an atom is, to tell if a molecule is ionic, polar, or nonpolar covalently bonded, we have to look at the electronegativities. And the electronegativity, if you remember, is the ability of an atom to attract electrons in a bond. So it basically means how hungry is an atom for electrons in a chemical bond. And so there is basically a ranking system where you could rank the most electron hungry atom versus the atom that basically doesn't want electrons at all. And so elements have been given a relative value ranking how strong their electronegativity is. As you've learned before in the periodic table trend section, fluorine is the most electronegative atom, and you see the proof here. It is given a value of 4, and hopefully you remember back from the periodic table trends unit, as you go left to right across the table, the atoms get smaller, and you should remember that smaller atoms tend to have a greater electronegativity, which is why this top right-hand corner, which is where the smaller atoms are, tend to have high electronegativity values. This other end here, which has the larger atoms, ones with the larger atomic radius, tend to have lower electronegativity. And again, electronegativity does not talk about the noble gases. So these values are going to be quite handy in determining whether or not molecules are polar or nonpolar. In IB, you are given a data booklet. The data booklet values are a little bit different than this, but they're pretty close. Okay, so in determining what type of bond, we have to look at electronegativity differences between the atoms in a bond. So let's just go through some of the scenarios here. If two atoms have a similar electronegativity, that means that they will have a similar pull on the electrons in the bond. If they're both got, both equally strong and pulling for the electron, then you have like kind of an equal tug of war. This means that the electron will spend almost equal time with each atom. So again, going with the tug of war analogy, it's like two strong teams, or I guess two weak teams, battling it out in a tug of war. The momentum in the tug of war goes back and forth, so no one side is going to overpower the other. That's kind of shown here. So here's dogs fighting it out with some bones. And as you can see here, the dogs representing atoms. The bone acts as the electron. There is an equal pull between the two dogs basically have an equal pull on the electron, and you have a totally shared situation there. If one atom has a large electronegativity than the other, then you're going to have a situation where one atom will outpull the other, and the electron then will spend more time with the other, with the more electronegative atom. So basically, just you can kind of think the more electronegative atom is stronger in the tug of war for the electron, and if it's faced up against someone who's got a small electronegativity or less power, it's going to, I guess like in a tug of war, drag it through the mud and win the electron. There's two types of this situation where one overpowers the other. Here you have the dog here, the gray dog, completely overpowers the yellow dog and takes not only its own electron, but takes its electron, the yellow dog's electron as well. And so obviously the chlorine, acting as the gray dog, has a very high electronegativity. The sodium has a very low electronegativity. So when they have the tug of war, the chlorine wins. In that tug of war, whoever wins the electron gets labeled as negative, and the one that loses becomes positive. You could have maybe not as lopsided of an affair. You could have, say, H and F bonded together. The fluorine has a slightly stronger pull for the electron than the hydrogen does, and because of that, the fluorine is just a little bit more negative than the hydrogen. Okay, let's go through all three scenarios again in more detail and not be so cryptic about it. Okay, so electronegativity differences govern what type of bond we're talking about. So the bigger the electronegativity difference, or E-neg diff as I call it, the more polar the bond is going to be. That's important. So what you need to remember, and you do need to remember these numbers, is this little chart here. So if you've got the two atoms, you look at their electronegativity. If their electronegativity difference, when you subtract the two electronegativities, fits in these different situations here, that dictates what kind of bond you're going to have. Okay, so if it's a small difference, they're both kind of equal in their power and their pull for the electron, it's nonpolar. If it's lopsided, you've got a very electronegative versus a low electronegative atom, it's ionic. The bond is ionic. Okay, let's look at ionic bonds in detail. And so the poster child for, actually before I do that, let's talk about what you probably learned before about ionic bonds. You were probably told before that ionic bonds are between metals and nonmetals, and you're probably expecting me to say that's wrong. Well, it's not wrong. It's actually pretty close. Think about it. Metals have low electronegativity, and nonmetals tend to have high electronegativity. They're on the right-hand side. Metals tend to be on the left-hand side of the table. And so, like I said, that's pretty much is the case. Metals have a low electronegativity. Nonmetals have a high electronegativity. So between them, there is a large electronegativity difference between the atoms. When that happens, that means the nonmetal, that's like the big gray dog, the chlorine in that little GIF that I showed you before, will pretty much have the electron all the time. And when an atom has the electron, which is negative, all the time, that will make it negative. And then, in that case, the yellow dog, the sodium dog, lost the electron completely. That means it makes it very, very positive because it lost that negative electron. Okay, now here is the example I was talking about for NaCl. So if I'm going to ask you, how do you determine whether a molecule is polar or not? These are the 5 steps that you look at. Actually, there's another step, another video about the Vesper stuff, but for now, just looking at the bonds, here's how you find out. So what you do first is you look up the electronegativities for the atoms involved. So we're looking at Na and Cl. So Na has an electronegativity of, as we look up sodium on, this is the IB version of this electronegativity chart. So sodium's got an electronegativity of 0.9, and chlorine has 3.2. So 3.2 and 0.9. 3.2 and 0.9. So we have 3.2 and 0.9. So we find the difference between them, the eneg diff, the difference between them. Use the subtract. And when you subtract the 2, you get 2.3. So 2.3, electronegativity difference of 2.3. Look back at that chart way back here, and 2.3, that fits here. It's above 1.7, which means that bond is officially ionic. So determine the bond by looking at it. Because it's 2.3, it is an ionic bond. Okay. Now, ionic bonds, like I've kind of hinted at here and there, have strong charges. One side is big time negative, one time is big time positive. So if I was going to show NaCl, the chlorine way overpowers sodium for the electron. So this chlorine is like big time negative and the sodium is big time positive. This is not the proper way to show it, but I'm just, for now, kind of give you an idea of what's going on here. Okay? And so there's NaCl, it's an ionic bond, it has charges. Now the question is the molecule polar? Well, according to the information we have right here, we say yes, NaCl is polar. And the last thing you might be asked to do is draw what's called a dipole moment. And a dipole moment, well, it's drawn like this. Here's the general shape of it. It's got a plus there and got an arrow right there. And so the dipole moment shows, it gives another indication of which side is positive, which side is negative. So the way you would draw this, that's the positive end, that's the negative end. So what you would do is you would go like this to show that this side, the arrow side, is negative, this side is positive. So all combined together, that's how you label the molecule, and you can identify its polar based on all this information here. Okay, and again, here's the ionic bond, Na and Cl. The Cl overpowers the Na completely, and the sodium doesn't see it at all. And as you can see in the charges, Na will become strongly positive, and the chlorine becomes strongly negative. And again, what happens in an ionic bond is those two opposite charges attract, and that's how they bond together. In a polar covalent bond, covalent means sharing, but in polar covalent there's unequal sharing. Here there is an eneg diff between them. There is a difference between the electronegativities in the atom in a polar covalent bond, but it's not as large as ionic. So because of that, the electron will spend slightly more time around one atom over the other. It'll spend more time with the more electronegative atom. And so because it spends slightly more time around one atom over the other, thus instead of strong charges developing, only slight charges develop. So how do you show slight charges? Well, here's HBr, and H has a lower electronegativity than Br. You can look it up on the table to verify it. And this little cloud here kind of indicates what's going on as well. The electron cloud is, you can see that the electron spends more time around the bromine than it does around the hydrogen. But it does go to the hydrogen every once in a while, unlike the sodium in the last example. So the electron is basically spending most time here, and then every once in a while it goes to hydrogen. Most time here, every once in a while it goes to hydrogen. And so because of that, slight charges develop. And the way you show the slight charges is this squiggly S, Greek symbol, okay? And that squiggly S, you know what, just for simplicity, let's just say that the squiggly S means slightly. It doesn't, and I'm sure chemistry teachers watching this will be rolling their eyes at what I just said, but just that little squiggly S symbol means slightly positive, and here, slightly negative. Okay, let's look at an example of a polar covalent molecule, which is water. I'm going to draw, I've already drawn here the Lewis dot structural formula for water. I did not put the Vesper shape structure in yet, the shape in yet. But for now, let's just look at it as is. So there's two bonds here. There's this bond there, and there's this bond here. What you do when you figure out if it's polar or not, you look at just the individual bond. So again, first what you do is you look at the electronegativity difference between H and O. And the way you do that is you look up in your data table, H is 2.2, O is 3.4, so 3.4 and 2.2. So that's the 3.4, that's 2.2. Please don't think, oh, there's two H's, I have to multiply them by 2. No, 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 no. It's each individual bond we're talking about. I'm going to focus on this bond right here. So there's the electronegativities. The difference is 3.4 minus 2.2. And that gives you 1.2. And 1.2, if you look back on the chart back here, 1.2, went too far, 1.2 is polar covalent. Yeah, here you go. So 1.2 fits in here, so it's polar covalent. Polar covalent. So therefore, it is polar covalent. The bond is polar covalent. Okay, now, how do I label the charges? In polar covalent, the electron spends slightly more time around the oxygen than it does compared to the hydrogen. And so the oxygen won't be big time negative, it will be slightly negative. And the hydrogen over here will be slightly positive. Obviously, the hydrogen on this side is also going to be slightly positive. So that's how you add the charges or label the charges. The dipole moment that we're going to draw, remember the dipole moment looks like this. That's the negative, that's the positive side. Let me just get rid of that. So it would be drawn this way. The arrows point towards the more negative thing. And for those of you that have done VSEPR, you're thinking, now I'm starting to see how VSEPR and the molecular shape of the molecule dictates whether or not the molecule is polar. And so that's what you would show there. Okay, so the bond itself, that HO bond, is polar. Now, as I've drawn it, is the molecule polar? Well, no, it isn't. They're actually canceling each other out, but I didn't draw it correctly. That's next lesson. I'll show you how to do that. So as is right now, there's a difference in electronegativity. It is a polar molecule. Okay, and then there's the situation then with the dogs. So technically, this dog here, because it has more of the electron, it's slightly negative, doesn't completely have it. And this dog over here is not completely positive. It still gets a little piece of the bone here, the electron, so it would be slightly positive. Okay, and nonpolar is the last condition where the electron is shared 50-50. So that means the electron spends equal time around each atom. So that because of that, there is no one side that's more negative than the other. So no charges develop. And that's what nonpolar means. No charges, pretty much. Yeah, there you go. And that was the first GIF that I showed you before about non-polar covalent bond. I can put non there, non-polar. The electron is shared equally, 50-50. No one side is positive, no one side is negative. There's no charges. So here's an example, oxygen gas. Oxygen gas, here's the Lewis formula for it. Double bonded oxygen. The double bond makes no difference here. There's electrons between the oxygen, this oxygen and that oxygen. And I believe, if I remember, the electronegativity of oxygen was 3.2. I believe it was. Doesn't really matter. Okay, so if that's 3.2, that is also 3.2. The E-neg diff between the two of them is obviously going to be 0. And because it's 0, that means there's equal sharing between the two of them. You have equally strong pull for the electron. So that means that this is a non-polar covalent bond. Now, if I'm going to add charges, how do I add charges to this? Well, again, the electron is shared equally, so the electron is going back and forth, back and forth, back and forth. Well, who has it more often? I don't know. It's hard to tell. It's equal. So you don't put any charges, so there's no charges. Because there are no charges, it is nonpolar. So it's a nonpolar covalent bond, and the molecule itself is nonpolar. Can we add a dipole moment to this? No, there's no charges on it. You can't label it with anything, with no dipole moments. You leave it as is. So a little summary. We'll just start with we started with the beginning. Ionic bonds, complete transfer of the electron, and what that does is it creates strong or full charges. The sodium never gets the electron. The chlorine gets it 100% of the time. So it's like, a sharing deal. It's almost like 0 and 100. Don't quote me on those numbers, but it's kind of just gives you a relative idea of what's going on with the electron. So you have strong charges, and so any ionic bond always creates a polar molecule. Same thing with polar covalent bonds. It's just, there is some sharing, but it's still unequal. And because it's unequal sharing, you have partial charges, or as I call them, slight charges. And my little silly little thing, that squiggly S means slight. And so instead of putting the big time positive negative, you have little squiggly S's there. And then non-polar covalent bonds, or where there, as you can see, there's no charges because there's equal sharing between them for the electron. So no charges develop. So this is a non-polar molecule. Are polar covalent molecules polar or non-polar? Well, if you're polar, you're either polar or you're not. You can't say it's slightly polar. So you would just say, yes, this is a polar molecule. So how do you create polar molecules? You need an unequal sharing of the electron. Okay, so these are practice questions. If I were to give you what type of bond is HCl, you would look up the electronegativities. I've given to you there. Find the difference between them. In this case, it's 1.0. 1.0 fits in the polar covalent range. And a polar covalent bond always creates polar molecules. So there's a difference between using the word polar in reference to polar covalent bond and overall saying if the molecule is polar or not. And if I would normally ask you to draw out the charges in the dipole moment, it would look something like this. The chlorine is more electronegative, so you put the squiggly slightly S minus there, and the S the slightly positive there, and the dipole pointed towards the negative chlorine. So for practice, I suggest you do these skill testing questions here, these 6. So with these 6, do exactly what I did here. Find the electronegativity difference, determine what kind of bond it is it polar, draw the charges, and the dipole moment. Okay, thanks for listening. Bye-bye.